I'm just going to pick up where I left off with the work energy theorem video. So we were just finishing up by talking about another way of viewing the work energy theorem, which is that the kinetic energy of an object is equal to the amount of work that that object can do before coming to a rest. And again, a way to think about this is if I had an object that was moving, right, which means it's got kinetic energy, and say it's got 100 joules of kinetic energy. If I want to bring that object to a rest, that means that I need to bring its kinetic energy to 0, right? But to actually bring its kinetic energy to 0, we need to do something with that 100 joules, right? And that something would be transferring it. So we could do work, right? So we could transfer this to other things. And if we give all that energy away, we can eventually get to 0. And that the amount of work that we have to do, right? The amount of energy you have to give away to get to 0 is equal to the kinetic energy, right? So that should make sense. And that's just saying, if I want to get rid of 100 joules of energy, I need to do 100 joules of work. Another way to think about it is if I had, a bowling ball that was going on a rampage and I was trying to knock down pins. Wow, it's a really bad one. I have to redeem myself. Yeah, this one's pretty bad too. Well, so there's like a bunch of these, and I have my bowling ball, and my bowling ball is trying to knock down as many pins as it can, right? So now when we look at the work energy theorem, the way we could see it is that the kinetic energy of the bowling ball is equal to the amount of work that it can do before it finally comes to a rest, right? It wants to knock down all these pins, and it can only knock down a certain number before it comes to a rest. And the amount it can knock down is connected to its kinetic energy. So the more kinetic energy it has, the more work it can do. So the more pins it can knock down. So let's do a quick numerical example of kinetic energy theorem. So say I have a ball that's initially at rest, and then we apply a force to it over a distance, and now it's going 10 meters per second, and say that this ball is 1 kilogram. And I want to know how much net work was done on the ball. And again, all we're going to do is kind of think about this in terms of the work energy theorem, which is the net work is equal to change in kinetic energy. And I'm asking you for the work side, right? So that means we have to calculate the kinetic energy side. So the change in kinetic energy, remember, is the final kinetic energy minus the initial kinetic energy. And if kinetic energy is equal to 1/2 mv squared, the final kinetic energy is going to be 1/2 times 1 kilogram times 10 meters per second squared. And the initial kinetic energy will be 1/2 times 1 kilogram times 0 meters per second squared. And that's going to give us 50 joules minus 0 joules, which is 50 joules. So we know that the change of kinetic energy is going to be 50 joules, right? So if this is equal to 50 joules, we know that the net work done must have been 50 joules. And again, that should make sense. If I got the ball to start moving, right, it initially had no kinetic energy, and then I got it to get 50 joules of kinetic energy, it had to get that energy from somewhere. Energy is conserved, right? Something is now out of 50 joules of kinetic energy. So the amount of work, the net work needed to be done on that ball has to equal 50 joules, right, at least.